Let's start with some simple example. A very simple example here. I have a current source IS, that's this guy, and then a network of resistances, capacitances, and impedances. So the time domain expression for the current source is given. It's a cosine, obviously. And then we are asked to find the voltage across this guy, across the 20 ohm resistance. What is the time domain voltage across the 20 ohm resistance? That's what we are asked to find out. And let's find out. It's a simple problem, as simple as it can get. Really, we have impedances in a time domain. Let's quickly convert them to frequency domain. Let me make a note of what we have available, what we have given, or what we have been given. Okay, let's see. We are given that I of S is this guy, meaning that the amplitude, okay, is 20 and the phase angle is negative 20 degrees. So if I am to find the phasor of the current, okay, the phasor of the current is really 20 angle negative 20 degrees, right? So all I have done is to convert this guy into phasor. Very good. Now, what else is given? Omega is given. Omega is given to be 52 pi omega, right? Omega is given to be 50k. That's this guy, 2 pi f. Okay, so given omega is 5 into 10 to the 4 radians per second. Okay, what else is given? You're given R1 value, you're given C value. Now, I think we have all the information necessary to convert this to a frequency domain. So let's do that. So I start with this, I copy this, and I'm going to leave the resistances as is because the resistances do not change in frequency domain. So this is going to remain 20 ohms, and this one is going to remain 1 ohms. Now, in place of 1 microfarad, I'm going to replace this guy with 1 over j omega c. Okay, 1 over j omega c. Okay, we know the value of omega. We know the value of c, 1 microfarad. Plug in those numbers. You will see 1 over j omega c. Now, what is this? This is the ZC impedance of the capacitance, right? So that is equals to 1 over j. Omega is what? 50k, 50,000. Okay, 50,000. C is given to be 1 microfarad, 1 into 10 to the negative 6. So you plug these numbers in, you should see a value of Z, 1 over j omega C equals to minus j 20 ohms. Okay, minus j 20 ohms. Okay, so that part I'm going to write here. This guy is negative j 20 ohms. Okay, that's the capacitive reactance. What else? What else we got? We have to take care of the inductance as well. This is this 40 microhenry, if I remember correctly, this is 40 microhenry. This can be replaced with J omega L. Okay, so we can find the value of J omega L, which represents the ZL, that is J times 50k times. The other guy is 40 microhenry. L is 40 microhenry. So this comes out to be, you can plug the numbers in. This will come out to be J 2 ohms. So this guy is really J 2 ohms. Okay. Now it's pretty straightforward from here. We have a circuit, okay? We have a circuit where the impedance values are known in the frequency domain. I'm going to pretend like these are resistances and then do the equivalent, okay? Where do I begin? Well, notice that this guy and this guy are in series, okay? So I'm going to copy this. I'm going to do a step by step just so it's easy for us to see, okay? Okay. Now, IFS is 20 angle negative 20. The voltage, we are interested in finding the voltage across the 20 ohm resistance. Really, we are interested in finding the voltage across this. Okay. So if we find the equivalent impedance of the entire circuit and find the voltage, then because it's in parallel to the 20 ohms, it should be the same. Okay. Since the impedances are parallel, we can assume that there is the same voltage. Okay. Now, the the first thing I'm going to do is to write this guy as 20 ohms in parallel with negative J 20 ohms in parallel with one impedance, okay, that is 1 ohm plus J 2 ohms. Okay. There is this current. Okay. So what we have is really three impedances in parallel. Once we have three impedances in parallel, we should be able to calculate the equivalent, right? So 1 over 20 ohms plus 1 over negative J 20 ohms plus 1 over 1 ohms plus J 2 ohms, all of that reciprocal, right? This is a parallel combination, pretty straightforward, right? Now we can calculate this to be 0.05 ohms, okay? 0.05 plus J 0.05 plus 0.2 minus J 0.4, okay? So all of this is inverse. Okay, so you can do the individual calculation. You'll see that it'll correspond to the same thing. You can multiply that by 1 over 1 plus j 2 omega. You can multiply and divide it with the complex conjugate 1 minus j2. Okay, you will see that it is 1 minus j2 divided by 1 square minus 2 square. Okay, so 1 over 5 will give you 0.2. 2 over 5 will give you 0.4. Okay, so it's a mathematical simplification. All I have done is to simplify mathematically the individual terms. This guy corresponds to this, and this guy corresponds to this, and all of this corresponds to this. Okay, so now I can go ahead and add these numbers up, and it will come out to be 0.25, okay, minus j 0.35, the whole inverse. So we are interested in all of this is what? Z equivalent. Okay, remember all of this? Z equivalent. That's the Z equivalent. Okay, let's see. The equivalent impedance of all the three impedances in parallel. Now, you'll see that this comes out to be, if you express this in the polar form, because you see there is 1 over 0.25 minus j 0.35, right? There is a division here. Division, you want to do it in polar form. So I'm going to write it as 1 over j 0.430 angle negative 54.46. How did I get that? Pretty simple. This part you will get by, remember, the square root of x squared plus y squared, where this is x and this is y. Okay, so this part represents the magnitude. The magnitude comes from the square root of x squared and y squared. Where is this part coming from? This comes from tangent inverse or arctan of y over x, where y is really this negative 0.35 and x is 0.25. Plug that into your calculator. You will see that the z equivalent in its polar form is 1 over 0.430, okay, 0.430 angle negative 54.46. Okay, now take the inverse of it. Or in other words, if you do this, if you do the division 1 over 0.430 angle positive 54.46, because when you're doing the division in polar form, you just have to do a subtraction. Negative of negative 54.46 becomes positive 54.46. So this turns out to be 1 by 4 turns out to be 2.325 angle 54.46 ohms. What is this? What does this number represent? This number represents the total impedance. Okay, if I am to have this 220 angle negative 20 degrees and one equivalent resistance, Z equivalent, that replaces all of these three impedances. Okay, then the Z equivalent value is 2.325 angle 54.46. Why did we get here? Why did we calculate this? Just so if we know the voltage across these terminals, that will be the exact same voltage across these terminals because it's in parallel. Okay, because a parallel, um, that is what an equivalent circuit means. So if we calculate the voltage across this guy, then I have the voltage that I am after, which is the voltage across the 20 ohm resistance. That's very simple. The voltage across across the 20 ohm resistance is the same as the voltage across the Z equivalent. Okay, the voltage across the Z equivalent, which is the same as the voltage across the 20 ohm resistance, is what? V is Z equivalent times I. Okay, from here it's a pretty straightforward math. 2.325 angle 54.46 multiplied by 20 angle negative 20. That's pretty straightforward. We know how to do this math in polar form. Isn't it convenient that both of these are in polar form? So multiply these two magnitudes, you have 46.499 or 46.5, and then you add these two angles because in polar form, when you're multiplying, you just add these numbers, which comes out to 34.46 degrees. Okay, you see, excuse me, I'm a little bit under the weather. You see, this guy is the answer that we are kind of after, V20 ohm resistance. 20 ohm resistance in its polar form, but we know how to convert this into its rectangular form, don't we? Once we not just rectangular form in the time domain form, all we have to do is V 20 ohms of t in its time domain form is I have the amplitude 46.5, okay, and then cosine, because this is a linear circuit, omega does not change, okay, 50,000 T plus the angle is 34 point, let me write this 3 a little better, 34.46 degrees. This is the answer I'm after. But if you think about it, besides the math, the logic of this is pretty straightforward. All I have done is to convert from rectangular to polar, from polar to rectangular. But besides that, it's just simple impedances in parallel, right? All right, we will do another interesting example.